Hello friends, welcome back to the channel. We are getting close to the end of 2024 and I wanted to deliver one last update and some information about the status of our DR.DRO device. I have some new features available in the software, and I also have some news concerning the enclosure and the displays, which I think you will find interesting. So in this video, we're going to go through some of these recent changes, and we will take a look at the new features available on the user interface. And then I will give you a quick tour of the new enclosure that I have designed for the 10-inch version of our display. All right, so let's take a closer look at this new version of our display, this improved model. You're looking at the back of it right now, and it's currently mounted on a very nice monitor stand, which has adjustable height, as you can see here, and it's very sturdy, it's very solid and robust. I will put the links down in the description and make sure you guys can see where to buy this product in our webpage, on the Provedo webpage. The price is very affordable and the construction quality is definitely there. There is a nice cable management solution on the device, which I think is very important, especially if you plan on installing this on a real machine. And yeah, the mount has the right size, which is 100 millimeters VESA mount. It has the right hole pattern, and I think also the right range for the purpose of the display on a machine. And as you can see here, this is the back of our new enclosure. It is a 10-inch enclosure rather than the 7-inch we have for the smaller version of DR.DRO. And the same ports are available on the back. We got our power supply plug here, which I'm going to connect shortly. There is a cable gland for the motor control device, and then maybe blocked by the view, but you can see a slice of it here. On the other side, we have the connectors for our linear scales and for our rotary encoders. This is how it looks like when it's mounted. I'm going to turn this around so you can take a look at the front of the enclosure. The models are all available online. You can get all the 3D printed models for the enclosure on my GitHub repositories. So if you want to print it yourself, you can go ahead and do it. And this is a 3-part enclosure, similar to the Wise Coco version we have for the 7-inch display. There is a front bezel, which mounts the monitor to the main frame. And then you got the rear cover, which has all the connectors. Let me see if I can show you the connectors on this side a little bit better. Yeah, there you go, you can see it. So this is what the display looks like on the left side. You have your 4 connectors for the linear scales and for the rotary encoders to be connected on this end. And connectors that appear on the other side are for power supply and for the motor control output. So let's take a look at our display now. Let's see, we got a lot of reflections here on this monitor. I want to see if I can maybe find a better angle for this. It's highly reflective. That's one of the things I like the least, but it might be also because I have the film that comes with the display is still on the display right now. Maybe once I remove that, it's going to look a little bit better. So you've seen the boot sequence, a few changes on that. This is the latest version of the operating system, the OSPI operating system, which is available on my GitHub repositories. Don't forget to give me a star there. I highly appreciate it if you could do that. On the new version, I'm using the latest drivers available from the Raspberry Pi Foundation. I'm using the latest kernel. I just recently updated the build process to use all the latest versions of the firmware and the operating system packages. So this should be the latest and greatest available for the 32-bits version of the Raspberry Pi operating system. And then on top of that, I do a few customizations with my custom version of the operating system, one of which is configuring the boot up logo. And then another one is configuring the serial ports and connections that are available from the Raspberry Pi board to the external world. And then I also configure the audio in a specific way in the operating system, which allows us to use the output that goes through the HDMI and therefore hear the beeps when we're using this type of Wise Coco display, which is another nice thing that the display has. It has two little speakers on the board, and you can use those to play sounds. So the way I'm using it for the DRO is to signal audio messages to the user. To give you an example, if I press on the gear, you can hear that the system is beeping. The beep volume is adjustable. I just went to the setup page right now. So if I go on the formats page, you will see that there is, of course, the usual section where you can configure how many digits you want to have for all your formats. On the display, you can change the color of your digits on the main page. And then you will see here there is a sound volume bar. And then you have this test button. And as you can see, we can adjust the volume. I'll show you a few different values. I don't know how easy it is to pick it from the recording, but you should see that the volume of the beep is changing based on the setting that we put on this volume bar. Let me go back now to our homepage, and I'll show you the rest of the features. So right now, you are on the home page. This is not changed much. I think it's about the same as it was last time we spoke. What has been changed is right now we can configure the DRO to work in multiple different modes. And those modes are available through this button here. Right now it says IDX, which is an acronym for indexing mode. If I touch this, we will get a secondary menu here that gives us three options that we can pick from. We can work in indexing mode, we can work in electronic lead screw mode, or we can work in jog mode. Jog was recently added as a separate page, but right now I changed the way this looks. I will show it to you in a second. And then the new one is the electronic lead screw mode, which is definitely a very convenient menu to have. I'm going to show you how the electronic lead screw mode operates and how it looks on the homepage. And there you go. So here we see our homepage. Right now there is no readings from the scales because they're disconnected, but we can reset it by pressing on the millimeters and inches button here. And here you see that we have our usual 4 linear scale inputs in here displayed. And then on the bottom we have a different ribbon, which is used to control how we want to feed, in the case of a lathe, for example, how we want to do the feeding or the thread cutting. And you have a few options available to you. So if we press on this button here, then we will be presented with a list of a table with all the options available to us for threading and for feed speeds. If you press on the top here, you will be able to select different tables that will show you some presets that I have configured in the system. Those are easily configurable in code. We can add or remove them or modify the values if I missed some. But in general, I have some of the most common threads for millimeters. We have a table for inches. Again, this is in TPI, so threads per inch. 64 is the smallest feed we can configure for this, and we go up to 4. Again, it's easy to add more. These tables are all dynamic, and we can provide a list of different values if we desire to do so. Then we got some feed, pre-configured feed values. We go from 1 thou per revolution up to 40 thou per revolution with variable increments. And then a similar setup table is also present for millimeters, where we can go from this is 100 microns up to, 10 microns up to 300 microns. So that gives you a decent range of speeds that you can use either in metric or in imperial if you prefer to do so. And the same applies to threading. So we got, threads for metric system as well as threads for imperial system. Now it's easy enough to select a value here. And what the system will do for us is it's going to tell us what is the currently selected thread down here on the bottom ribbon. You can see that. We see that we are in thread inches mode. We see a current relative position of our lead screw. This is mostly useful for troubleshooting for myself, but it might have some good use also for the operator. And then we have these 2 big buttons here that allow us to change on the same table. So right now we are working with the inches threading table. We can press these 2 buttons to go to the previous or next setting compared to the one that is currently selected. So We can go back and go up to the fastest one, sorry, the smallest increment one, which is 64 threads per inch. And as you can see, when you change the value here, when I change and I select a different TPI, what this ELS mode does for us is that it sets automatically for us the proper ratio for the spindle, okay? So this last value here that says S on the display, this is the spindle input, which is an encoder. It's a rotary encoder, and it's configured to tell us, right now it's going to give us the revolutions per minute, which is the default for a spindle mode axis. And as a consequence, we select and change the values on the axis that is configured in spindle mode with the value that is selected for a specific thread or a feed value. Let's do it for a feeding in millimeters, for example. If we select here, I don't know, let's do 100 microns, for example, you will see that in this case the ratio goes to 1 to 10. So the meaning of these two numbers is the ratio that we need to apply to convert from the metric to the imperial system, which is 254 divided by 10, so 25.4, that's our ratio. And then on top of that, we have the ratio which we want to apply for threading in inches, which is 1 divided by 13. I will give you a few more examples of the settings that we can apply to this, and I will also connect a rotary encoder to the spindle axis so you can see how the system operates and we can try to make a sense of this. Let me go ahead and grab a rotary encoder, which I have right here. Okay, this is our rotary encoder. It will simulate our spindle. I'm going to connect it to the spindle input right now. There we go. So let's make sure this guy works. Right now I have it in debugging mode. So on the second line you see kind of an absolute position of the spindle, which never resets. Let's see if we can get this to work. It appears there is something wrong in there. We need to change the ratio. Let me configure that real quick. So we want ELS mode, we want this one needs to be 800. That is correct. We want to set lead screw in inches, yes. And then this should be all there is to it. And on the scale, we want to use denominator. Oh, that's our problem. So we need to do 4096 here, and then spindle mode. Yes. Okay. There we go. Let's see. Okay. That's more like it. Okay. So yeah, the second line on the display right now is going to show us the absolute position between 0 and 360 for the positive numbers at least. And then on the main row we have our current speed, which is a moving average. It has the last 4 or 5 values in the averaging, so it doesn't jump around too much. So we got our speed, we got our position. Okay, I'm going to zero this, and our current position here is already set to 0, so we don't have to worry about it. Let's take a simple case. So we will set our system to operate in inches. This display here, this value will actually report to us the advance on the lead screw in inches. So as soon as I enable this guy, we will see that this number advances in correlation to the position of our spindle. Let me keep this to 0. So let's select our spindle as our input for our calculations. And now let's see what happens when we advance. I'm going to try to stop around 1 full revolution, which is 360 degrees on the second line. And what we want to verify and confirm is that we advance 1/4 of an inch, because we have selected a threading cycle that requires 4 threads per inch. So as you can see, we are a little bit past 360 degrees, and indeed we have an advance on our lead screw of 0.2519, so close enough. Now let's do the same thing in reverse, and let's go back to 0, for example. So we want to see minus 360 over there. Let me see if I can center it close enough to 360. Got there for a second, but course, it's very hard to get it the right number, but as you can see, it's all working as it's supposed to. Let's keep going here. Let's do a few revolutions. And you can see that the feed is advancing as expected. We got our numbers rolling correctly. The current position is reported as it should be, and everything is working as we want it to work. So let's do a few more tests now. I'm gonna reset our axis again here. Okay, let's go set this to 0. So we got our current position set to 0. We got our axis set to 0. Let's go, for example, and use a let's do a 10 TPI, right? 10 TPI, we got our ratio configured correctly. So what we expect to see now, let me reset this. I must have moved it inadvertently, but so position is 0 and spindle position also is 0. So now we're gonna go and we are gonna advance on our spindle. We're gonna do one full revolution again to verify that everything is working correctly. And as you can see, our advance is exactly 0.1 inches, okay? Now let's do, for example, let's go and use the feed in inches instead of using threading. And let's do 10 thou, okay? Let's do a 0 again on both our axes. And let's try to do the same exercise. We're gonna go ahead and do 360 degrees. Let's see if I can get it. 360, well, that's close enough. And as you can see, we got 10 thou of feed on our lead screw, okay? So one nice thing about the display is that it will work fine and it will not care which unit you're selecting. So if I go, for example, in millimeters, you will see that the current position is properly translated into millimeters. It's 254 thousandths, which is exactly what we expect to see. And we can also work, for example, use a metric feed or a metric thread while the display is reporting to us inches. So let's do an example in millimeters, just as a last one, to give you guys a bit more of an understanding of how this thing works. So I'm going to go ahead and select here our feed. I'm going to do threads in millimeters. I'm going to select, for example, let's do a 1.25, which is a pretty common one. So I must have selected the wrong one. Let's see. Okay, 1.25. So we got our thread selected here. We got our ratio set, 5/4, whatever number is needed by the ratio. It's calculated by the system. So we have our axis zeroed. We are displaying units in millimeters. So we expect to see 1.25 here on the display once we complete a full revolution of our axis. So let's go ahead and run our spindle. There we go, close enough to 0, I guess. There we go. So as you can see, it's a 1.254. You know, again, it's very hard to stop exactly at 0. My encoder is also bumpy for whatever reason. I think the bearings are not great, but you get the concept, right? It's working as it should. So this is working as expected. Now, one nice thing, which is very useful, especially when you are doing feeding. Let's go and select, for example, a feed rate of 50 microns, right? Let's do a 0 here again, and let's 0 our axis as well. So I'm going to use two hands here just to show you how this works. But so right now we are spinning our spindle and we are feeding our feed rate, as you can see here in our current position. And let's say we want to change our feed rate while the machine is operating. We can press this button and the system will update automatically the feed rate and will update the configuration of our ELS mode dynamically without having you to stop the spindle mode or without having to stop the synchro mode. So this can be changed on the fly, and it will make it much easier for the operator to find out what's the best feed rate and speed that needs to be applied on the workpiece to get the finish desired and to get proper chip breaking, for example. So this is a nice addition that on a manual machine you would not normally be able to do. So that wraps up pretty much all the aspects and features that I have so far implemented on the ELS. There will be more. Some things that I want to add in here, for example, are the end stops, and I want to also be able to automatically pick up the thread if you disengage the F nut and you retract your saddle to the starting position. That is something that definitely can be done because we have our inputs that tell us the position of the saddle. We have our input telling us where the spindle is, and we know exactly where the axis needs to position the tool to restart threading our part. So I definitely want to get those things in place, and I also want to put the end stop, so it's going to be much easier to machine down to a shoulder. But for now, this is all we have, and it's definitely better than nothing. So let's look at our next mode, which is not really a completely new feature, but it's definitely something that was not finished. It was not fully tested and implemented on the previous video. So if I press on my mode setting page again and I go to jog, I now see that on the bottom of my page I have a series of values, and I have all the controls that allow me to do jogging on my axis. And I have added in a couple of things compared to the previous page. We didn't have a max value, we didn't have the acceleration value. So now it's much easier to know where we are with the system. And then I also moved over here the position, the current position for the axis. We can also, not yet, not in this version. I will make this resettable and configurable from here like we have on the other pages. But right now we can just press on this guy and say, okay, give me 5,000 for my desired speed. And then when I press start, the current speed will report to us what the current speed is for the axis. And we can go ahead and change this dynamically without having to stop our cycle. We can change the speed, we can change the direction as well by changing the sign of our number. This will generate the proper ramps and go and accelerate and update our position correctly and do all the controls as usual. Alright, so we are back here at the DR.DRO from where we left before. I want to show you guys now the settings page because I have made some changes on that. Let's go ahead and take a look. Let's start from the top. So setup page, the layout is the same as before. We got our linear scales or rotary encoder inputs on the first 4 buttons. They are all identical and there is no major changes in here. We already had spindle mode configurable before. There are literally only 2 values that you need to configure based on your machine. So what I typically do is first I set a name for my axis if it's not set already. So we are looking at scale 0, I think. So I'm going to call this one X. And yeah, that's X. And then you have ratio numerator and ratio denominator. It's quite a simple way to set up these guys. The only thing you have to do is you need to provide a ratio for the units that you are displaying. And you can set your resolution or your accuracy based on the scales that you have, and it can be whatever you want. It can be microns, it can be tenths of microns, it can be bananas, it doesn't really matter. The important thing is that you know what the ratio is supposed to be between your linear scale, which normally has a tag with all the specifications and all the parameters in it. For example, a commercial glass scale typically is 5 microns per step or 1 micron per step. So if you have a linear scale, it is 5 microns per step. What you want to say is that you travel 5 1,000ths for each step of the scale. And these are the 2 numbers that you want to set. Now, in case we had, for example, a 1 micron scale, then you would type 1 in here, and this would say that for every step, what we need to advance in our units is 1 1,000th of a millimeter, okay? This is how the system is configured to operate. Now let's take a look at the scale number 3 on my display, which is the spindle scale, okay? In this case, what the system wants to know is the ratio, or let's say the number of steps that it takes for the encoder, like this one, to run a full revolution. That's all it needs to know. So 1 represents the revolutions in our system, which is 1 in this case, and then 4096 is the number of steps that this specific encoder takes to perform a full revolution. And how did I get to that number? Let me show you on this specific encoder, because it might be sometimes misleading, but if you look at this encoder, in this specific model here, it says here resolution. This encoder, for example, says in here that the resolution is 1024 pulses per revolution. So why did we set it to 4096? Well, the reason for that is because encoders give you the resolution in full quadrature mode. But because of the way the inputs are configured in our DRO, we are actually using a 4x encoder mode, which means that the number you see printed on the encoder needs to be multiplied by 4. So this becomes 4096. The other thing you have to remember to do is, of course, to set this axis in spindle mode. And that will tell the display everything it needs to know to handle the input coming from this encoder. And when you configure the axis as spindle mode, the main page will display the speed in revolutions per minute rather than showing you an absolute position, which would be pretty useless in the case of a spindle. Now, moving on, the next page that you will see has a few changes is the servo settings. On the servo page, you have a series of values in here. We have a gearing ratio on the top. We have speeds configuration, that is depending on the motor you have for your servo axis. And then you have an ELS mode setting section, which is the portion that I have added here. What is the ELS mode allowing us to do? Well, all these values you could have set conveniently on the gear ratio on top and in the units per turn, but I think it's easy to forget how these numbers have to be calculated and how to set them up. So what I did is I made a convenience list of fields here on the bottom that allow configuring the lead screw pitch and the lead screw steps instead of having to configure a ratio. So what do we have here? We have a pitch which can be specified in millimeters or in inches. So if I deselect this flag here, then the number I enter here is going to be for a metric lead screw. For example, I can say that my lead screw is 4 millimeters per revolution, and that will set all the ratios correctly for us. Or I can do I can specify my value in inches, in which case I would have to specify my pitch as a pitch in inches in here. As you can see, the only thing that changes here above is that the ratio is accounting for the metric to imperial conversion, but much easier to have it set with a flag rather than having to calculate the numbers manually, okay? So if we look at this, when ELS mode is selected, we can specify our pitch. Let me go back to a 4 TPI lead screw, for example, and that's gonna give us the proper ratio. So what we're telling the system is what is the pitch for our lead screw, and then we're also telling our system how many steps of my motor it will take to do a full revolution. And this, again, will depend on how you set up your lead screw. You might have a lead screw that has gear reduction between the motor and the lead screw. But let's assume everything is in the simplest of possible cases, where we have the motor connected directly to the lead screw, and our motor is configured with a normal value with some level of microstepping, which is 800. And these values, by the way, are configurable on your stepper motor driver or on your servo driver. You have usually dip switches or parameters that you can configure on your unit to tell the unit how many steps you want to pulse through in order to do a full revolution of your motor. So in my example, I'm assuming 800, but it can be anything. You could have it set up for example, I don't know, 1600. And you just set the value in here, and you just need to check and verify, make sure that indeed 1600 steps will do a full revolution of your lead screw. As long as that is true, then the system will calculate and work and do exactly as you expect it to do. So again, very simple. We can change this. We can say my lead screw is a metric and is a 4 millimeter per revolution lead screw, and it will adjust the ratios for you. Or you could say my lead screw is an imperial and I have a different ratio for it. And then the last section that I haven't spoken about is the one that allows you to configure the parameters for your motor and your drive. So this is something you need to figure out empirically, because it will depend on how much load you have on the motor. It will depend on how big is your motor. It will depend if it's a servo or a stepper motor, so too many variables. But in general, you have two values that you can play with. One is a number of which configures the maximum speed of your motor. And 10,000 seems to be a good value for my rotary table and for my motor. And then you have another value which allows you to configure the acceleration. And 10,000 is conservative for me, but you can set 20,000, for example. And this again is in steps per second square. So these two values allow you to tune and find out the best performance for the reliability that you want based on the motor that you're using. And it's important that you set them depending on how you configure also your stepper motor driver in case of a stepper motor. If you do micro stepping and your motor does, for example, 6,400 steps per revolution, then you will definitely have to increase the speed, otherwise your motor will move very slowly. You can go much faster with your steps per second, and the same applies to the acceleration, of course. But if you're instead going with a smaller number of steps per revolution, then you definitely have to decrease this, because physics will catch you. The motor will not be able to go as fast as you want it to go. Probably the stepper driver will be able to send out the signals, but the motor will not be able to keep up with it. So in my case, I normally use between 400 and 800 and occasionally maybe 1600 steps per revolution if I want some more positional accuracy. So in that case, normally between 10 and 20,000 is a value that I can support with my motors. But again, it will change and it will depend heavily on what type of drive and what type of motor you have in your system. So that's pretty much it, and as you can see, there is still a few bugs and things I need to figure out in this page. It's definitely not finished 100%, and I also would like to hear your thoughts about it, so maybe we can improve and make this thing look a little bit better in the future. But it definitely works, and the calculations are good, and the system is working very reliably. So we have just made a change here, so let's see how that is reflected in our homepage. There should be no difference, of course, but let's just take a look. We just changed our lead screw from a 4 TPI to a 4mm lead screw. As you can see, the ratios are the same as they were before. And now when we rotate through this guy, of course, if I reset my axis, it's probably easier. Let me select this. This will not change, of course, because the only thing that will change when you adjust your parameters for the servo motor is the amount of steps that we send out to our stepper motor driver. So you don't see any changes in here. But if we had a real machine attached to the display right now, then we would see a difference in the way that the machine moves, and we would see a difference in the ratio. But yeah, this hasn't changed from before as expected. And we can go ahead and change between metric and imperial to see our current position, adjusted accordingly, and everything seems to be working fine, at least in this beta version of the software. So if you're interested to hear more, please let me know. Leave me your comments down below. I will try to get this mounted on one of my lathes as soon as possible, so we can do a real live video and see some real applications of the ELS mode, and then I will see what you guys have to say about it, and based on your feedback, continue the development of our display, and I will continue adding features and functionality to it. I hope you enjoyed the video. I hope you enjoyed all the updates, and I will see you the next year.